So I really only have a couple of slides of kind of review to go over. I want to show you one calculation that you're not going to need to know yet, but you eventually will. And then I have a link to another animation that I like our old textbooks online features that they go over. Again, what you're going to see is we're going to cover thermodynamics this first semester, and then the very last thing we come back to second semester before studying for the AP exam is more thermodynamics. Heat and energy relationships are often a complicated topic for students because it's hard to visualize the movement of heat. Plus, when we start talking about energy involved in chemical bonds and then how the breaking of those bonds, the forming of those bonds can cause heat to either be gained or lost as well, creates some confusion. But typically what we're looking at is the net change of things. Again, when I mentioned that we're going to be in the lab the next 3 class periods, you're going to see examples of heat being transferred from one thing to another. It could be something as simple as putting a hot object in a cold object. It could be something like mixing up a solid. So dissolving salt changes the temperature of the water. Well, we have to be able to explain why. Chemical reactions changes the temperature of a solution that it's in, or just the reaction itself. So you saw vocabulary like system and surroundings in the reading guide. Again, I'm not going over that. Endothermic and exothermic, hopefully that is reviewed for you. The one other thing that you hopefully already written down, so maybe you don't even have to jot this down, is a reminder of the first law of thermodynamics. Energy can't be created or destroyed, just converted from one form to another. Second semester, we go over the second and the third laws of thermodynamics as well. But again, if we're trying to kind of follow the path of the text, we cover enthalpy mainly in this chapter, which is what I'll define in the next slide and show you a video of.
I heard splitting atoms makes a lot of energy.
So, nuclear chemistry is the exception to this, yes. So, fission energy, when you split an atom, will create energy, and there's a little bit of loss of mass. Fusion, same thing. The sun gives us heat and light because of 2 hydrogen atoms fused together. A little bit of the mass is lost and converted to energy. I mean, that's your Einstein equals mc squared. Nuclear chemistry, which is what that's referring to, is a very minimal, if any, point of emphasis at all on the AP exam. So I know in Chem 1 we cover that a little bit. Actually, this year in Chem 1 we're changing it because we're going to cover that at the very end of the year. Because once we introduce that to students first semester in Chem 1, they start thinking that that can happen in normal chemical reactions, and it can't. So that, true statement, but at the same time, if we're not dealing with nuclear reactions, we don't have to worry about that. Enthalpy is just a fancy term for the quantity. So the numerical value. So in other words, the math that we have to do that shows heat changes. Anyone in here physics too? So you're going to be doing some enthalpy stuff at some point too if you haven't already. And in order to make physics interesting, they have to teach chemistry from time to time. Just like in order to make biology understandable, they have to teach chemistry from time to time. Chemistry is to science what moles is to all math in chemistry. It's just the most important one. Or wrap up notes, rather. So again, here is a question. Again, each class period I'm going to be introducing you to more and more enthalpy math as we move along. So this one is dealing with a chemical reaction and is almost stoichiometry-esque. So again, how much heat is evolved, so given off, when 266 grams of white phosphorus, P4, burns in oxygen to form tetraphosphorus dicoxide, and it gives you the enthalpy for that reaction. A couple things to note before I go to the smart notebook and show you how to solve this. We talked about diatomics in Chem 1, but we don't talk about things that are even more so than that. Phosphorus typically is not a single atom of phosphorus in nature. It's P4. So don't be alarmed that you see this subscript and nothing after it. Again, Chem 1, we tried to keep things simple and accurate at the same time without overburdening students. Sulfur is another example that you wouldn't see sulfur typically on its own. Sulfur exists as an 8 sulfur unit to be one thing at that point. So again, what you could see is it in word form. Otherwise, a very common way to see this problem. So remember, beginning of the year, I said, hey, you have to know how to write formulas for stuff, but equations are commonly given to you. It's very common that it would give you the reaction. So P4 plus 5O2 yields P4O10. It's very common that you'll be given an equation, and then right after it, and maybe there'll be a tab to give a little bit of space, it'll give you that delta H value, that enthalpy value of negative 3,013 kilojoules per mole. What that value means on that side is if I had one P4 in this reaction, that's how much energy would be given off. So if I had 1 mole of it, it would give off, and the reason why I say give off is it's a negative sign, it would give off a little over 3,000 kilojoules. If I had 5 O2s, it would give off that much then as well. The question isn't saying necessarily that we have 1 mole of P4, because if we had twice as much P4, and then everything else we had as well, it should give us twice as much energy. Does that make sense? If we have twice as much of a reactant and it reacts, it should give us twice as much output. I mean, 1 log versus 2 logs, which one is giving us more energy when it burns? So how you would approach this question is you're given 266 grams of the P4. When in doubt, what do we do? Convert to moles. This needs to be the mass of 4 P's. So 123.88 is what I have written down. Just like a diatomic, you probably saw this on the web sign with the gases. Diatomic, you have to do the molar mass of both Cl2, both O2. We have to do this for P4. Notice how grams would cancel out then. You could solve this, which by the way, if you solve this, I believe it gets you 2.15 moles. However, what you would see in my notes of how I do it, how the textbook probably does it as well, is we can use this enthalpy value as a conversion. Because look at what unit we're in right now when grams cancels out. We're in moles of P4. From there, all I have to do then is say there's 3,013 kilojoules for every 1 mole of the reaction. And since there is a coefficient of 1 in front of the P4, that's all we have to do. If there's a coefficient of 2 in front of it, we'd have to do a little stoichiometry. Like there's 1 reaction for every 2 P4s. But now, moles cancels out. And it would give us kilojoules, our unit of energy, as our final answer. Negative 6,470.